You have lots of time. Hey. Hello, volleyball. Today we're talking about something that's a little bit weird, but it's kind of a three-stage thing where we do Lewis dots, and Lewis dots show us where electrons spend their time. Then we're going to take a step forward in that, which is called Vesper or Sepper theory. And what it's going to do is going to show us how a molecule is actually shaped. Then we're going to take both of those concepts and we're going to use them to look at polarity a little bit. And it's kind of like you learn to run or learn to walk, then you learn to run so you can play basketball. It's sort of the same idea where you learn Lewis dots so you can do this. And once you can do this, then you can figure out polarity. And polarity actually explains a lot about how things interact with each other. By the end of that lesson, you'll be like liquid nitrogen. Totally makes sense to you why it behaves the way it does. So it's kind of this weird in the middle step. And it's a little bit abstract for students because it has to do with repulsion forces and things like that. But there are some really wonderful computer programs that can help you to understand it. So I'll do a bunch of examples with you, but hopefully you leave at the end of class, the next hour, whatever, understanding the idea that electrons will repel each other and will cause some unique shapes to happen. That's the primary goal, I would say. So if you go on your document, you should have something that looks a little bit like this, okay? And the very first thing is that this word, actually don't know how to pronounce it properly. I always say Vesper, but I think that's a James Bond reference. It stands for valence, shell, electron, I just put E minus, electron pair repulsion. Okay, which is a fancy way of saying electrons repel each other, which you probably already know, but it actually impacts the shape of a molecule as well. Okay, so the first thing I'll do is I have two molecules here, and it says I'm going to ask you for their Lewis structures. Okay? Maybe as a bit of a side note, if you guys think back to grade 9, maybe you drew Bohr models of water. Your teacher probably drew them like this. Yeah, that's how water looks. Sometimes you draw Bohr models, they call it Mickey Mouse ears. I've seen this before too. Here's your oxygen, then your hydrogens are like this. It looks kind of like Mickey Mouse. Yep. And I had a student this year in Science 9 ask me, well, why is it not in a straight line? Why is it in a weird bent shape? I said, that's actually, we talked about that in Chem 11. Because there's things going on, there's forces at play there that are going to cause that shape. But we'll start with these two right here, which is CO2 and SO2. So CO2 is carbon dioxide. You might know this one in your notes already, but for Lewis structure, it's like that. And SO2 looks like this. Okay. Now, if we do the math on these molecules for our Lewis structures, we're going to find that they both want 24, all right? Because 8 plus 8 plus 8. This one wants 24 as well. But they're not going to have the same number of valence electrons to contribute. Oxygen has 6 because it's in the 16th row. Carbon only has 4. So oxygen is 6. Sorry, carbon dioxide is 6 plus 6 plus 4, which is
16.
16. Beautiful. Nice work. Just always encouraging you, Brendan. Get that on video. All right. So we have 4 bonds to work with because we have 16 or 24 over 16 is 8. Divided by 2 is 4. So we're going to put 2 double bonds. And I think you guys did this one in your homework questions already on Lewis structure. Am I done? Is that the Lewis structure done?
No.
Not quite. Why not, Ava? You're right.
You need to balance them out. So you need 4 dots on both oxygens, and then there should be 2 dots on one of the lines from each side, one on each side.
Beautiful. I actually don't need to draw the dots on the lines. I just was when I was explaining it. But this is perfect now. It's good. Okay. So if we check there, this oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. Remember we said carbon likes to form 4 bonds? Oxygen likes to form 2 bonds. You probably could have not done the math on this and guessed this was what it looked like, but the math always makes sure it's right. Yep, that's correct. That's what CO2 looks like. The actual shape of CO2 looks like this. Right there. And you might go like, well, what the heck, why did I do all that work? Because it does matter to try and go from here to here. That one makes more sense. The next one will make it a little more obvious. We'll do the same math. How many valence electrons does sulfur have? Yeah, 6. Same as oxygen. They're in the same family, right? So now we have 6 plus 6 plus 6, which is going to get us to 18. 24 minus 18 is 6. 6 divided by 2, not 3. Divided by 2 equals 3. And so we end up with this weird scenario. We have 3 bonds we have to use. but we already have 2. It doesn't matter which side you put it on. I'll put it on that side right there, but it doesn't make any difference, honestly. Okay. And we got to finish this thing up. So we have oxygen here with 2, 4, 6, 8. This oxygen only has 2, so we go 3, 4, 5, 6, 7, 8. And this sulfur has 2, 4, 6. We're going 7, 8, like so. And that would be the Lewis structure, SO2. Now notice that earlier, carbon likes 4 bonds, oxygen likes 2. Oxygen likes 2, it doesn't have it in this case. In this case, this oxygen has a single bond. This one's double bonded. Sulfur also likes 2 bonds, this one's triple bonded. Has to do with electronegativity. When I remember I said earlier that there's all kinds of rules in chemistry, and then fluorine shows up and just changes them all. Things that are very electronegative change the rules. All right? It's kind of like, I don't know, you're grade 3, you're the fastest runner in the class, everyone knows it. New kid comes to town, changes the rules. It's faster than you. How you like that's the exact same thing happens in chemistry, where the rules get changed when very electronegative elements come into play, and oxygen and sulfur are both quite electronegative, fluorine more so even. So you're trying to work at those patterns, but they don't always work. Okay? The shape of this guy is not a straight line. This is correct. I drew it as a straight line in my Lewis structure because I didn't know any better. But now that I see it looks like this, I'm actually going to change it to look a little bit like the water molecule looked like this. Okay? And I'm going to explain this via this little program right here. So I'm going to draw carbon. I'm going to do carbon dioxide for a sec here. Okay? This is carbon dioxide. There's a carbon in the middle, and there's oxygens on either end. The oxygen dots don't matter. We really only focus on the shape around the central atom. Okay? Bigger molecules, you go to university, there's like computer programs you can use to solve for the whole molecule. But for now, carbon's here, oxygen's here, oxygen's here. What are these bonds made out of again? Electrons, right? And all electrons are negatively charged. So what happens is, as you have these electrons here, they have the same charge, and therefore they repel each other as far as possible. Okay? You can see, if I put a bond angle on here, show bond angles, you can see it's a 180 degree bond angle. Even if I mess with it, I can try and make it shorter, like try and put them together, it eventually bounces back to 180 degrees. Because that is the farthest apart that those electrons can repel each other. Try to put 2 magnets that are not like 2 negative magnets are together, they will immediately flip around because that's how they repel each other. Okay? Which tells you this is the shape of CO2. Now, if you look at the Lewis structure we drew for SO2 around the central atom, 1 double bond, 1 single bond, and 1 lone pair. Okay? The shape changes. The shape right this is actually, the last one was called linear. This one, some of them are like really like trigonal pyramidal. This one's called bent, which makes sense. So it's a good name if I ever figure that out. Okay, but it makes sense. Now you have 3 zones of electron concentration around the central atom. You have this double bond, you have this single bond, and now you have this lone pair, which is also made of electrons. That's the little 2 dots. I don't know why they give a little alien face here, but you have 3 areas, and now you're trying to separate 3 zones of negativity as far apart as possible. They'll naturally repel each other. Okay, and so if I go like this, right, and I bounce it around, doesn't matter, I can flip it upside down, molecules move in space. But no matter what, I can try and put them together, but it'll always bounce back to 120 degrees because that is as far apart as you can separate 3 things around a central atom. Okay? So this is what we call it valence shell electron pair repulsion. It's a fancy way of saying this repels that, which repels that, which repels that, so they all spread out as far as they can. Okay? This is why it's good to the video, because I think this lesson is a little bit like abstracted out there. Alrighty, so if you go back to here, okay, the document, that's why I drew like this in the actual shape. You don't actually need to include your lone pairs in your shape, but I drew it in a bent shape because I knew that this single bond, this lone pair, and this double bond right here, they're all going to repel each other. Okay, so I knew they would end up like this. Where this one, there's only one area of concentration of electrons and another area here, and I knew they were already repelling each other as far as possible around the central atom. But you can't figure this out unless you can draw Lewis structures, because you can't figure out what's around the central atom unless you know the Lewis structure, which allows you to figure out the shape. The shape tomorrow, or on Thursday, sorry, tomorrow's Tuesday hour. On Thursday, the shape will come into play with how it responds in terms of other atoms and other molecules it interacts with. Okay. Let's go back to this little app here for a second. So let's just let's try this right here. If we have two atoms, we can say, Mia, what's the bond angle between two? If we have two areas of concentration? Yeah, 180, perfect, right? Cole, if we had a third one, what's the bond angle gonna be?
120.
Beautiful, 120, right? Keeps going the pattern, keeps going Berlin. If we have a fourth one, what's it gonna be? Should write some notes here. What's the fourth one gonna be? If we had a fourth one, fourth thing separated around it.
90.
No, 109.5. Okay, good try. I was just setting you up there. Okay, we always forget that it's three-dimensional. All right, so there's no way every year I basically just pick on someone to guess that, laugh when they guess 98, and then pick up a random number like 109.5. Okay, you're not gonna know that. We always forget molecules are three-dimensional, right? So like, it makes sense that, sorry, it's a double bond here, but around one we can have 3, 1, 2, 3. But if I change this up, right, and I put single bonds on here, down this molecule, so here's one right here, and then here's another guy right here. That's a weirdly long one, but whatever. Okay, but now you can see it's 3 degrees, so it's 109.5 degrees as far apart as they can get, because there's a positive, or there's a north component to this, and there's a slight southward to each of these, but that's as far apart as you can separate the four things. Okay. So really what we're looking at today then is just looking at examples and trying to figure out their shapes. Okay. So the key to this is that bonds will move as far apart as possible. So we look at the central atom and we say, okay, what's happening on the central atom? Let's move everything around it in order to make the shape of the molecule. Bonds and lone pairs are areas where electrons are considered concentrated. Right? We know that electrons are actually jumping away and closer, but the area where they're spending most of their time is where they're concentrated. And since they carry a negative charge, they will repel each other and occupy positions around the central atom so they can be as far away as possible from each other. That's their job. Get far away from each other. Okay. Now what we'll do is we'll look at a bunch of different parts, a bunch of different ways that they interact with each other from a distance. So the first one was two areas, electron configuration. This is the one where I was just picking on you guys. Okay, so we have two areas, right? And that's going to be 180 degrees apart from each other. So we say down here, two areas are going to isolate or separate 180 degrees. Three areas, we said 120. And the fourth area is that weird 109.5. I'm guessing in 10 years of going over this, no one has ever said 109.5. I don't think that's a commonly known fact that in a 3D object that four things can be separated. I didn't know that until I tried it on the program the first time I heard it, I guess, but okay. I would have said 90 as well. Alrighty, so here's how it looks. We're gonna build a little just examples basically. Okay. And we'll go from there. So for the Lewis structure, I'm just gonna draw X's and Y's. Okay? So the first one says two areas of electron concentration. I'm gonna put an X here, and I'm gonna put double bonded to a Y, double bonded to a Y. Okay. The molecular shape of that is gonna be the same, just like carbon dioxide. And maybe for the sake of just seeing it, when I see two areas, two bonding areas, they're right here and right here. Students often think, well, that's not two bonding areas, it's four. We're not looking at how many bonds there are, we're looking at areas where electrons are hanging out. So electrons are hanging out here and here, that's two areas. And there's no lone pairs on the central atom. So those are gonna repel each other as far as possible, right? Which is why we get the same shape. We call that shape linear. It's a straight line. You see, oh, this molecule has a linear geometry. Carbon dioxide has linear geometry, just a straight line. Okay? The next one we'll try, okay, is when we have 3 bonding areas. So we'll do this. We'll go X, we'll double bond it to Y, single bond it to Y, single bond it to Y. Now you might be asking like, okay, well X has 8 electrons, 2, 4, 6, 8. Why not Y? We could add the lone pairs on Y, but we're only concentrating on what's happening around the central atom. That will determine the shape, right? If you look at this thing, what determines the shape is how far apart the bonds are around the central atom. When molecules get bigger, then you got to like treat them. This one is central, then this one, then this one. You figure all the shapes around all of them and put it all together. But when we're only looking at simple molecules like in Chem 11, we just figure out, okay, around the central atom. So if you want to, it bothers you to not put like 2, 4, 6, 8 dots. Or down here it'd be 2, 4, 6, 8. But here it'd be 2, 3, 4, 5, 6, 7, 8. But the reason I'm not doing that is because I'm focusing on the central atom only. So here we got 3 areas of bonding. We got one here, and one here. And when there's 3 bonds and 0 lone pairs, the shape, you can see I kind of naturally already drew it that way because I knew that would be the case. Okay, and we call that shape trigonal planar, aka a triangle on a flat plane. Okay, it's a triangle and it's on a flat plane, like this. Yeah, I'll go here a second. If I go here, voila, I have a triangle and it's on a flat plane. If I turn it, you can see that's a flat plane right about there, right? There's no 3D sticking out of the board or anything component to it. No matter where I put it, it's a flat plane triangle. So trigonal planar is not quite as cool a name as bent, but there it is. All right, and then the last one is the one we just did. I'm gonna go, let's go a lone pair here. Let's go a Y here, and then a double bonded Y over here. This is like SO2. The actual shape though, those things are gonna repel each other more than that, so it's gonna be like this. And we call that shape bent, which is what SO2 is. That's a bent shape right there. Bent. Is that so bad you can't read it? Jade, I see that. Nice writing.
No, your linear was a little odd. Ooh, that's good penmanship.
Bent. Very neat.
I can read it.
My tetrahedral looks terrible too now. Look at it. The R is like just like a little dangler on the A there.
H is just an L.
False.
Tetrahedral.
It's like a little bit of. Yeah, it's not great. Penmanship has never been my strength. All right. Now we're going down to, so that was 3 areas. Now we're going down to 4 areas. So that means all the areas around the central atom are occupied because 4 areas means 8 electrons. So the first one we'll do is just X, Y, Y, Y. Okay, a lot of Y's. Now the shape here is going to look a little weird because if I go back, oh yeah, sorry, and I'll do the same thing where I forgot to do this, sorry. 2 bonds and 1 lone pair. There's the lone pair right there. And now we have 4 bonds, so 1, 2, 3, 4. That's awesome. Maybe it'll come back, maybe it won't. Check the terminal. You want to, Cole, sit in the chair and just give the things in the back a wiggle. The connection's not great. Yeah, just start wiggling. Oh, maybe not.
It's because you told me to.
Yeah, the threat of, we're good, we're back. All right.
He's getting ready.
It's like a small child. Like the threat of it happening was enough for it to figure it out, smart it out a little bit.
Oh, this one is tetrahedral.
Thanks, Cole. All right, so we're gonna go back to here for a sec. Okay, I'm gonna add a 4th like I did before. We get that weird 109. Okay, 109.5. Now this thing right here is 3-dimensional. And we draw in 2D on paper. So what I'm gonna do is I'm gonna draw it in kind of a way that will look a little bit weird at first, but I just wanna try and like help you see kind of what it is. So right now, just pretend with me, this thing is straight up and down, this one right here. Like this is, say it's methane, CH4. So C, H, 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 H. This one's straight down. This one is pretty much straight this way as well. It's flat on the board, right? If you kept going, it'd be flat on the plane of the board. This one is clearly heading towards Cole and Emilio. Okay? This one is heading towards the hallway on that side of the lab. It's back into the wall. So we actually have a method of drawing this where we can show when things are coming towards us and when things are leaving away from us. So when we go to our little drawing here for this molecule, what we do is we go, okay, there's an X, oops, I'm using the wrong pen there. There's an X here, there's a Y here, there's a Y here, okay? This Y right here, you draw a little triangle and you shade it in, okay? And what that means is, that guy is coming out of the board at you. He's aiming towards you. This one's flat, this one's flat, this one's aiming towards you. And then the last one, we're gonna put a dotted line, and in chemistry that indicates is it's going away from you, like into the board. Okay? So if we look back at our little thing here, this one's, I can aim more like this. Okay? This one is coming straight towards you. This one is going back into the wall. That's the dotted line. This is the triangle we fill in. This one's kind of flat. Now, you could also make it so one comes towards you and two go away from you. That's kind of like right here. This one's coming towards you. That's also correct. You just got to make sure you actually choose a format that is correct, right? If I aim this one right at Evan, right, the other two are going that way and that way. So you can also have one coming out, but just like for sake of learning, and I think it's easiest just to pretend that one is flat, one's coming at you, one's going away from you.
What do you mean flat?
Like it's flat on the, if you're drawing on paper, and the paper's right here, right? This one is flat on the paper. This one is flat on the paper. This one's going into the paper. This one's coming out of the paper. Yeah. So that's how we draw with that. Like that's the little triangle, that little dotted line. Okay. We call it tetrahedral because it makes a tetrahedron, right? Which hopefully makes sense as well. Let's try another one here. We got X. We got 3 bonds and 1 lone pair, so we'll go Y, 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 and lone pair. 3 bonds, 1 lone pair on the central atom. Okay. Our actual shape of this one's gonna be like this. X, we got a Y, we got a Y coming out of the board, and we got a Y going into the board. We just don't have the Y on top because we have a lone pair there instead. Right? Because this molecule only has 3 atoms around the central atom, 3 Ys around the X. So if we go to here, I'm just going to steal one of these bonds and stop a lone pair on there instead. And you can see we have the same molecule we just had. Now kids will ask, like, what if it's upside down? Yeah, you can draw upside down. This is also the same thing. It didn't like, if this is a poisonous gas, this is a poisonous gas. Right? If this is, I don't know, a component in aspirin, so is this. It's the same molecule. I haven't changed any bonds or anything. It behaves the same way, and they are floating in space. It's just nice to have a standardized way to write them. Right? That's called a trigonal pyramid, or a trigonal pyramidal, some people say, but it's a triangle pyramid. I was trying to think of it from a simpler sense. Triangle pyramid makes sense to me. Okay? And then the very last one, we're going back to bent shape, but it's going to be a little different, because this bent shape is X with a Y and a Y. So 2 bonds and 2 lone pairs around the central atom. So there's my 2 bonds, my 2 lone pairs. I'm still highlighting, so here we go. 2 lone pairs, 2 bonds. And that one's gonna look bent again, the same as before. The bond is a little bit sketchy like this. Making it really neat this time. There you go. Merry Christmas. Okay? Bent. So that one's also bent. If we go back to our little piece here, you can see why it will look very similar. So we're gonna take one of these bonds away. I'm gonna drop an extra lone pair. Drop 2 lone pairs on there, and you can see if I line it up right, it's because we don't care what the lone pairs in the drawing, but you can see the 4 areas, this bond, this bond, this bond, this bond, this lone pair, they're all repelling each other, and it ends with the bent shape. This is actually what water is. There's a question on your practice quiz yesterday. Explain why water's bent shape is crucial for life on Earth. That's what we'll talk about on Thursday. But if water was not bent, all water on Earth would be gaseous, which would mean we don't drink it, which would mean all kinds of problems. We couldn't have blood because blood is all water and water is liquid. And all those things boil down to the fact that water has this shape. It's actually like essential for life on Earth, right? If you think about it's H2O, so H, and then the O is going to have 2 bonds and 2 lone pairs. This is what water looks like. All right. So again, the goal for today is just, if I give you a molecule, can you do the Lewis structure? After that, can you then identify, okay, it's a Lewis structure. Now what? Now how do the bonds and electrons repel each other? What shape do we end up with? Okay. You guys have a bit of time. Oh, here's there's water right there. Look at that. Real molecules with the proper color and everything. What else they got? NH3. Nice. Okay. And then you have, so what you guys do is to fill this next page in, but skip the very last part. Don't do the polar or non-polar. We're going to add that element on Thursday, but just fill in the other pieces right now. So draw the Lewis structure, draw the areas of concentration around the central atom that says, draw the shape, and then name the shape using what you just, the sheet just made. That's good. I'll keep it on just in case.